Okay, so yeah, just to finish this bit off, we are basically trying to get to a position R on the plane. So let's say that's here, okay? Now, we're at a point that is on the plane, that's point A. Well, what we can do is we can go down here and up here. So this vector here, R minus A, is how I get from a point I know to any point on the plane. Okay, so R minus A, where A is a point I know, to get to any point R that I want to know. Now, what I know is that the normal of R minus A, if I use, because it's a normal, if I do the dot product of that, that must be equal to 0. Okay? Because any two perpendicular vectors have a dot product of 0. And just a little bit of algebra here tells me that this is going to be n dot R minus n dot A equals 0. And so then rearranging, n dot R is equal to n dot A. Now, I can sort of visualize this a bit better if I say that it's that R times, let's turn it around, is equal to x1, y1, z2 is equal to x2, y2, z2 times x1, y1, z1. Okay? And what we can say about that is that x1, y1, z. Sorry, I don't know why I've done it like that. X1, y1, z1 is a vector normal to the plane. Normal to the plane. Okay, and x2, y2, z2 is a point on the plane, or a position vector of a point on the plane. Okay, I hope that makes sense. So we've got another equation that helps us to express a plane. Okay, and the beauty of this way of doing it is that we can use this method to find the Cartesian equation of the normal of a plane. Okay. So let's just have a look at how that is done. Let's say we have a plane that has a normal vector of A, B, C and passes through X, Y, Z. Well, that means that, so let's use the equation we just had. We can say that any point on the plane is A, B, C times dot product with a point that is on the plane, X, Y, Z. Okay? And so this any point that is on the plane, we can just change this R, because R is going to represent any point that is on the plane, will be just X, Y, Z. Okay? So remember, A, B, and C, and capital X, Y, and Z is just a number. Okay, that's just going to be a number. But the left-hand side is going to be dot product to that. It's going to be AX plus BY plus CZ. And on the right-hand side, you're going to do the dot product, but it's just going to give you some number. We'll call that number D. Okay, so this is the Cartesian equation of a plane, and can be found most easily by using the normal equation of a plane. So when you look at the Cartesian equation of a plane, A, B, C is a normal vector to the plane. Okay? So here's a question. Find the equation of the plane with normal vector 1, 2, 3, which passes through the point minus 1, 2, 4. So using the normal equation of a plane, we know it's going to be x, y, z, that's your r, times the normal vector of the plane is equal to the normal vector of the plane times the point that is on the plane. So just using dot products, we're going to get x plus 2y plus 3z equals negative 1 plus 4 plus 12. So x plus 2y plus 3z is equal to 15. Okay? And that is the Cartesian equation of that plane. Okay? Find the equation of the plane that has these 3 points in them. Okay, in vector form and Cartesian equation form. So we've got a plane and it has 3 points, A, B and C. So let's just do it like this. Let's go A, B, C. So if I want vector form, I know that it's going to be this. It's going to be x, y, z is equal to vector, a point on the plane. So there's going to be minus 1, 2, 0. Let's pick A. Plus a vector in the direction of AB. So AB is going to be 3, 1, 1 minus 1, 2, 0, which is equal to 4 minus 1, 1. So it's going to be plus some amount, lambda, 4 minus 1, 1, plus mu in the direction of A to C. Well, A to C is simply going to be 3, 0, 1 minus 1, 2, 0, which is 4, negative 2, 1. So 4, negative 2, 1. There is the equation of the plane in vector form. Okay? Now in Cartesian form, what we need to do is find the normal to this plane. So my pen is about to run out, so I'm going to stop the video, charge my pen up, and I'll finish the question off.